홍보는 여기 지금 사람이
내려가는 거 이거 한다. 아, 이게 빨리.
네.
또 안 됐어요?
안 되는. 여기서 해야 돼.
위에를 제가 삭제했더니 안 됐더라고요.
된거 같은데.
Okay, it's time to start. Today our speaker is Professor Changhyun An from Gyeongbuk University. This is very exciting topic. Recently, very interesting. So it's a nice chance to hear from the expert, Professor An. So please start.
Thank you for your invitation. So I will present today on celestial holography. I think, yeah. Yeah, so, okay, so also I present at several places, so let me just mention here. And this is for colloquium. Kookmin University via Zoom. KNUT, again last January, and also 2022. I also present similar topics at NYU. Okay, so as in abstract, I will talk about the following things. So starting from the introduction, and in section 2, this is for bulk theory, and section 3, I will describe the two-dimensional conformal field theory, and also in section 4, celestial amplitude and also the celestial OPs. And finally, in next section, I will also describe the soft symmetry, and so my recent work, and I will describe the open problems at the end. Okay, so my motivation was based on the this paper, the Preminger W1 plus infinity and the celestial sphere. So I just quote some Penno's text book, The Road to Reality, and we can think about the celestial sphere somehow. I was infinity limit, and at the origin where the Earth is located there, and we have some hemisphere, and also if you just go the other directions, and then you will see the whole sphere. Okay, and this is for also the I prepared for the colloquium style, so maybe you can just skip some of the slides. So it is the concept of holography and conformal field theory. Let me just mention that here we have the dilation and special conformal transformation, and conformal transformation is somehow preserve the angles. Okay, so what is the main proposal is given by, can be characterized by this following statement in here. So in 4D case, we have the asymptotically flat space-time, and we want to understand what is quantum gravity in this theory. And also the corresponding two-dimensional theory is given by this so-called celestial component theory. And it appeared maybe 17, something like that. And we want to understand what is quantum gravity, and by using this hologram. And we have some experience from the ADS-CFT correspondence, so we want to understand what is the symmetries behind this kind of new holography. And here I mentioned that here the Stremingers he wrote some books, but you can see that there is some other useful exercise and problems and so on in here. And there are various lecture notes and some various places, and mainly I'm interested in the Fum's lecture notes. Is basically my presentation is based on her lecture notes, and also she will talk about the standard ICT lecture this year, and also so some Simon Foundation collaboration. You can find some information in this particular site. And last October, there was some kickoff workshop there. Okay, so now let me just start with. So I will explain what this picture means in my presentation. So this is for introduction. So I will go through the next section, IR structure of the gravity. So in order to understand the concept of boundary, somehow the people try to describe our space-time in finite region. So here we have the Minkowski metric in here. By using the spherical polar coordinate system, you can rewrite in this way. And as in electrodynamics, we can introduce.
About this Sequest talk, or you're doing more serious things? You remember there was this talk that you said it's nothing.
Yeah.
So I was just curious. Well, I mean, it's on for 3 minutes now. Yeah. Okay. I don't know if it's interesting.
Okay, then we have the retarding time, and still we have some infinite range. So so we have this kind of metric, but we know that the tangent function is somehow located between -π/2 and π/2. So we have, by using this change of variables, one can rewrite the previous metric is given by this one. So you can see that the capital U and V, we have this kind of simple form. Furthermore, by introducing this linear combination, we will end up with this metric in here. So the one-dimensional RT, and we have the three sphere. Okay. Then you can just simply, we can cut this piece, then we will get the next picture in here. So this is somehow the standard Penrose diagram for the Minkov space. So we have, so our null boundary is given by this one and that one, and this is spatial infinity and timeline infinity. And also one can have this kind of picture there. So we have here the previous null boundaries and timeline, past and future, and the spatial infinity in here. So the point is somehow we are talking about the massless particles. So graviton, photon, and gluon. So somehow coming into this region and then go through in here. When this massless particle hit this R=0 region, and then it goes through in this way, so 45 degrees, and go to the null boundary in here. Yeah.
Why the particle reflected the particles and in passes?
So in here, if you just extend the half of the diagram, then you can maybe figure out the massless particles somehow go through in here, and there is some scattering appears, and then you go through in here and in here. But if you have only one half of them, then somehow this is somehow maybe our location, and this is the past infinity. So some incident particles coming from the past, the infinity, and some interaction appears in the our place, and then gets scattered and goes through the other it goes through the other boundaries in here. So yeah, because we should have somehow, this is a massless particle, so you can just imagine at each point we can draw the light cone one. So that means we should have 45 degrees, and then also it should move in here. So but massless particle case, so you don't have to worry about that one. So that can be any trajectory. But for the massless particle, I mean, this is the only way trajectory you can see. So also you can have the massless particle from here to here, and then again the same kind of picture. Okay, so this is what I meant in previous picture. So we have the massless particle, and we can start at the past null infinity, and then R=0 case, we have somehow those massless particle is moving to future null infinity. So in this case, capital U and capital V are located at finite region. So that's what the Penrose did in previous work. Okay, so for the massive particle case, I don't consider in this presentation, but also we can there is some relevant work in recent times. And here is the usual angle dependence coordinates, Z and Z bar, and north pole, south pole. And one of the coordinates that in two spheres is given by previous rectangular coordinate x1, x2, x3, and also a radial coordinate in here. So somehow we want to understand the S matrix somehow that evolves in incoming states. on the past null infinity and to go outgoing states on the future null infinity. And also I realized that Perry's black hole lectures, maybe you can see that the YouTube, and he explained all the detailed discussion or within 1 hour lecture here. So it's very useful. Okay, so Poincare, this is for the colloquium stuff, so we can skip this slide. And here our Minkowski metric by using this rectangular coordinate system. So this is retarded time, and we have the z bar and radial coordinate. So this is so you can check the using the previous the Minkowski metric. Using this relation, you get this expression. Okay, so now we want to understand the effect from the gravity. So all the so we have some radially outward spherical things and fluctuate, and we somehow studied asymptotic flat space-times. In here, the so-called Bondi-Sachs coordinate, we can just rewrite the previous the metric is given by this one, and we can use the Bondi gauge, and also we want to understand the 1/r expansion around the Minkowski metric, and we just study those behavior near the future null infinity. Okay, then for given the constant u, the retarded time, and 2 sphere coordinate z bar, and we have additional r coordinate, r goes to infinity limit, we want to study the behavior of the metric in here. And in 1962, the BMS group, so one of them in here, and the single also in here, the SAS, they found this kind of non-trivial metric components, and we have the MB in here, and C, AB, and NA. They play the role of the important physical quantities. So again, here we notice that the gravitational radiation still is present on near the null future null infinity, and this is the previous coordinate for the rectangular coordinate by using the previous u, r, z, z bar. Yeah, so this somehow I mentioned 3 quantities are so-called this radiative data, and here the NP is somehow the energy density, and this depends on our angular coordinate z bar in here. And another quantity NA is somehow the angular momentum density, also depending on the angular coordinate z bar in here. And also lastly, we have the gravitational radiation in here, so the so-called Bondi-News tensor. Capital N is given by this relation. So you realize that in electromagnetism, we know that field strength is given by the derivative of the vector potential. So we have similar analog in here. This capital C satisfies some traceless and symmetric property in here. And due to this energy angular momentum, then we have the conservation for the energy momentum and also conservation of this angular momentum that play the role of in this context. Okay, so now we need to understand what is asymptotic flatness. So in usual terminology, we have this eta is a Minkowski metric, and Lie derivative will give us zero values killing vector equation. On the other hand, in our case, we have for given metric G, we need to require R goes to infinity limit. This Lie derivative approach to the zero. This is our asymptotic flatness condition. Okay, so now through the various complicated computations, they found the BMS. They found this vector field or whatever it is, the Poincare generators or generalization of Poincare generators. So you can see that all the terms contains round Z bar, round R, round U, and complex conjugation, and similar thing happens in here. So the first part contains the capital Y, and the second part we have the small f in here. So in terms of those the bonding coordinate U, R, Z, Z bar, so one can easily check if we take the small f and capital Y as some particular unit, the finite terms, then we will reproduce. We will obtain the known Poincare generator. In other words, the translation and Lorentz generators. Okay, so now the super translation is somehow the generalization of the previous ordinary translation. So you can see that in this vector field, the f contains f depends on the angular dependency explicitly. So in that sense, somehow we have the infinite number of symmetry appears in this context. So direction independent means we have the two sphere coordinate z bar in here. So we have in general, this is somehow the contains the ordinary space-time translation, and also this is a generalization of ordinary translation symmetry. This is somehow the previous from the previous Penrose diagram. We have two sphere looks like this one, and each point this arrow has different sign and different direction. Okay, so now the yeah.
How many number of symmetry or Turing vectors are remain comparing to those in flat Minkowski space time? When you think about the PM.
Yeah, so in Poincare case, we have 6 Lorentz generators and 4 translation generators. So totally we have 10. Right?
But in this case,
in this case, we have the infinite number of symmetries. Yeah. So you can choose f with any function of z and z bar. So that's what I mean is infinite number of symmetries. So I will show for the example of the f is some simple form. Then you reproduce the previous Poincare symmetries, Poincare generators. But in this description, the f can be any function of z bar. So in that sense, we have the infinite number of symmetries.
Your third term here has a positive power in R. Is it okay?
This one, right? Yeah, so one of our behavior behaves, I mean, different, term by term, it behaves a bit differently. So I think I mean, it doesn't spoil anything.
But when you plug this expression into the killing equation, I will not get any positive power in R.
No.
Only negative.
Yeah. Okay, so
But are you talking even with the 1 over R term, we have infinite dimensional symmetry, or only R goes to infinite limit we have? What is the statement?
so we should have this relation, right? So we have basically the metric was given by this one, and so what I'm saying is 1/r squared. The order by order, you need to somehow satisfy the previous Lie derivative acting on the metric should vanish. So if you consider 1/r level, then all the expression should vanish because we should have Lie derivative acting on the metric should vanish.
number does not mean that you know and it depends on the killing rate of the overcome 10 and so space time shift keeping this time shift. If you think about this kind of thing, then the number should be reduced to from the 10 to a small number. Maybe the symmetry is something different to what I think and
Yeah. Yeah. So what I'm saying is you get the infinite number of those previous whatever it is, f small f and y. So we have you can expand some spectral harmonics, for example, two sphere, then you get the summation, domain summation goes to some number 0 to infinity. In that sense, we have the number of the generator or symmetry is infinite. Okay, so in other words, somehow by comparing the general relativity and special relativity, there is some difference appears in this BMS construction. This is some short notation for the Poincare group. So we have for the BMS, we have infinite number of symmetries, somehow generalization of the Poincare groups, so where we have semi-direct product of the Lorentz and super translation. Okay, so if you consider this kind of combination, linear combination or fractional form, then you get the usual translation for the time and space coordinate. And also, if you consider capital Y as this form, then you get the 6 generators of from the Lorentz transformation. Okay, so now for the capital Y part, we have so-called super rotation. So it appeared maybe after 50 years later. So capital Y is the vector field on the two sphere. So you have the capital D is covariant derivative acting on the two sphere here. Yeah, so by this group, 2010, and BMS can be described by this simple terminology. Okay, then we allow this capital Y somehow the Meron function with some finite number of poles, and then we can generalize the previous this piece any monomial. So that's the K. The K can be any integer number. Then you get so-called extended BMS given by S. Here we have the super translation, but we have
infinite symmetry is a local symmetry or
local symmetry. Yeah, so local
without gravity.
Gravity is. I'm talking about here the 4-dimensional theory. So still we have in our universe, in our space-time, we have the gravity, right? So
no space-time is actually not coupled, gravity coupled, no coupled.
But but still we at the origin we still have some matters. I mean, due to some gravitational interaction, but near the boundary, the future null boundary, still we have some gravitational radiation.
Then you mean the metric you answer your answers satisfy the Einstein.
Yeah, Einstein equation, yeah. Yeah, that's right.
And by tensor is non-zero.
Oh, yeah. Yeah, I didn't mention the Einstein equation. Yeah, it satisfies the Einstein equation. Okay, so then you get, by allowing the actually the power within this one, then you get this local conformal group is given by our known the Virasura left and right, and here is still we have the super transaction. Okay, this is so-called the people they called it as the extended DMS.
And in the previous page,
Yeah.
the arbitrary function f of z bar in the previous page, f of z bar is arbitrary function.
Yeah, arbitrary function.
Yeah, so it means a gauge artifact. We can gauge away. So how to determine the arbitrary function? Using boundary condition, or we can gauge away? In local theory. In the local theory, there are two ways. One is to gauge away, and the other is using boundary condition.
I think maybe it is related to boundary conditions. So
Boundary
yeah, I didn't mention that the past null infinity and future null infinity. I mean, between those, we should have some conjugate quantity, and you need to somehow construct the conjugate charges, and inside the integral, then you need to impose you need to use the boundary condition between those two null boundaries.
Yeah, there is this independent conjugate charge that corresponding to the different f functions. So there are
What are correspondence?
corresponding to the f function.
Function f plus, f minus.
Response to
Yeah,
conservative.
in the user gauge theory, actually the global charge doesn't depend on the gauge function. But in that case, actually the conjugate charge depends on the f functions. So there are an infinite number of the different independent conjugate charges.
Then conservative
So,
charge depends
yeah,
on
yeah,
arbitrary function.
Yes.
Conservative quantity depends on arbitrary function.
Yes.
But you need to integrate over the two superiors and so on.
Right. Yeah.
Not unique. Is it closer? Not unique. Conservative quantity is not unique.
There are infinity.
Yeah, infinite number. Yeah.
I have a very simple question.
Yeah.
Do you consider something very poor or application very good influence in some clinical time? Well,
In asymptotic flat Minkowski split. So we are talking about the two null boundaries.
When you think about application real answer and statistical analysis, but non-zero bidimensional equation, non-zero bidimensional.
Yeah, indeed.
It could be related to communication rate or from.
Yeah, in this case also the condition for the biotensor should be used. I mean, in
So I asked.
yeah. Also, the biotensor behaves. I mean, in each component depends on the what one of R in there. Yeah. Okay, so furthermore, these people they try to understand by relaxing the previous factor in here. So y is function of any z bar function, then we get this so-called generalized BMS. But yeah, I should mention that basically this BPG paper is very well known in CFP paper. So this kind of things maybe after 20 years later, I mean, they studied the two-dimensional. This is for purely the two-dimensional analysis, but somehow the celestial holography people, they found somehow the 4D description can be related to this 2D description in here. And also this diffeomorphism is somehow rather non-trivial things and still ongoing subject in here. So I just mentioned that this is so smooth super rotation and so on. And also one of the main things also in general context, he somehow constructed this II triangle that is related to memory effect, asymptotic symmetry, and soft theorem in next picture. So during last 10 years, people this is some the four-dimensional theory, and today I will just talk about only this soft theorem and the corresponding 2D CFT in here, but through this you can go from here to here and so on. So asymptotic symmetry, what I mean is the super translation, super rotation, and this can be related to the order identity, and also memory effect can be related to this one through this picture. And yeah, so the we have the soft photon theorem. We have also soft graviton theorem. The super translation, we have the reading soft graviton theorem. For the super rotation, we have subreading soft graviton theorem. And as I mentioned, Poincare to be generalized to BMS. In this case, extended BMS. In other words, Lorentz goes to 2 Viragers. Okay, so the goal is somehow we want study from the experience of the ADS CFT and how the holography works in this bulk and boundary theory, and the Weinberg, and basically he somehow computed the quantum gravitational scattering at a very low energy behavior. Okay, so this is somehow the end of the this is the colloquium stuff. So we have some memory effect. So basically that's somehow the change of the gravitational potential. And yeah, so we can have some connection between the memory effect and the symmetry of the space-time by studying signals from these binary black hole mergers and so on. Okay, so this is for the 4D theory. So any questions, comments?
Yeah, I have a question.
Yeah.
We believe that ADS-CFT is actually non-quantum theorem.
Uh-huh.
But in your talk, the asymptotic symmetry just tells about the radiation factor of the gravity. So
Yeah.
what is your expectation of the non-quantitative aspects in this celestial holography?
I will maybe go on the chapter 4 or chapter 5, and I will describe some operator product expansion of, so-called celestial conformal field theory. So in that case, those OPE or commutator or anti-commutation somehow non-perturbative effect, and also those soft theorems somehow the reading and subreading, they are universal behavior. So and we think that at some point we have some non-perturbative description. So of course, in the bulk theory, we consider the asymptotic flatness condition, but basically the symmetry behind this holography is somehow related to the non-perturbative behavior. Maybe after I will finish, then maybe if you have some further questions, and then I will just comment on that.
So you mean that by the subreading correction, you mean that the final R not infinite R?
That subreading is related to the energy of the massless particle, soft particle. So R is our bonding coordinate, radial coordinate, but the subreading is in the sense that when you expand those amplitude in terms of the omega, so the energy. So subreading means omega goes to zero limit, so it's different from R goes to infinity or is different limit.
So still you are working on the R equal infinity.
Yeah, that's right. So we are in the future null boundary. Yeah. Okay, this is also we can skip. Yeah. So the point is the isometry of the Poincare is given by this isometry of the Minkowski space is given by Poincare. So we have a 6+4, and you can easily understand this Lorentz group is given is same as the SL2C divided by Z2. So you can check the number of generators in 6, and here's a 6. So we can if we just look at the general relativity book, and we get we have the 4 different kinds of the Lorentz group, but we can simply choose this kind of particular one. And SL2C in the usual CFT textbook, you get this kind of things. So we have here, maybe next page. So we have that dilation, rotation, and spatial conformal transformation that can be understood by this kind of transformation. So A, B, C, D satisfy this condition. So the point is this SL2C divided by Z2 is somehow the group of conformal transformation on the Riemann sphere. So the Riemann sphere is nothing but our celestial sphere. So complex plane plus Z is equal to 0 point. Okay. So in other words, this Lorentz transformation is nothing but the conformal transformation of the celestial sphere, and we can apply the standard Lorentz transformation, and we want to rewrite all the coordinates in 1D coordinates in terms of this in the conformal basis. Okay, then so we want to understand S matrix in the SL2C covariant form, and we need to use different bases, so-called boost eigenstates. So in the left slides, I will explain this one. But if you just consider this null vector in here, and by taking this wave function, then you can check the here is the usual rotation and boost in terms of those conformal notation L0, L plus minus, L0 bar, L plus minus 1. So you can easily see that this is a relation, and then you can get this eigenvalue equation. So in other words, the K3 acting on phi is proportional to the boost weight. In our case, the conformal dimension in 2D in English. And also you can check this one and that one. So that's imply highest weight with respect to S was 1,3. So in that sense, we have somehow the boost eigenstate is the correct basis, and we can associate with 2D dilation is related to boost in the 4D, and also the rotation goes to rotation, 2D and 4D relation. And this is somehow the explicit relation, that dilation and boost too, and this is a rotation. Okay, so now we can introduce null vectors given by this. You can see that this is related to previous rectangular coordinate x1, x2, x3, and also other components. So you can you can see that this null momentum is given by each component is related to our z coordinate in two sphere. They transform in linearly by using this SL2 transformation. We are talking about the massless particle in 4D sense, and we have graviton, gluon, and also scalar field. Then you can introduce some scale for the energy because we want to take this omega goes to zero limit. And if you are familiar with left and right-handed spinner, then this ratio somehow is related to our coordinate in two sphere. And you can for the Feynman diagram, we have the incoming. For the outgoing, we have to assign the signs there. And we in amplitude community, they somehow this spinor notation is very useful. So here's some dictionary between the two regions. The bulk case we have 4-dimensional theory. We have some particle, the energy for the massless particle, and 2D case we had a boost weight capital delta in here, and also we are talking about the graviton case. We have the plus minus 2 helicity. Gluon case, we have the plus minus 1 helicity, and scalar case, we have a 0 helicity. That is related to 2-dimensional the spin J here. So this is very important two dictionaries. So in other words, momentum eigenstates, the standard usual the basis. This is somehow is not useful for this highest weight representation. So we need to go from the standard momentum eigenstate to the boost eigenstate. Okay, so we should somehow introduce so-called Mellin transform in the scattering process. As matrix, this is also we can skip the for the QFT we only know about the electromagnetic weak and strong, but we should somehow understand the gravitational force. Okay, so now by changing the basis, we have basically the S matrix in the boost eigenstate. So here this is the explicit transformation. So for given plane wave, you obtain this kind of wave function. So I use this one in order to explain the boost eigenstate. And yeah, also this is the standard Lorentz transformation, and also other transformation in two sphere coordinate. Okay, so now the celestial amplitude is somehow by multiplying those each integral piece. So you have the omega j in here, and this is turns out it is interpreted as the boost weight in here. So you have this is so-called celestial amplitude, and moreover we have so in the SL2C covariant formalism you get this so-called conform primary wave function. They transform according to this SO1,3 and also Z-bar rotate the transformation, Möbius transformation. And also we can construct somehow these boundary operators characterized by this capital delta, capital J, and I think the spin, and also the incoming, outgoing, the notation, the plus minus sign in terms of this some integration. This is rather technical things, but anyhow, so you have for the in-state and out-state, you can just simply multiply this Mellin part, the integral of omega. So then you get this kind of relation here. Okay. So any questions about the 2D stuff?
So what is the symmetry of asymmetrics here? SL2C?
You have S matrix written in terms of the momentum, each momentum, P1, P2. But momentum is somehow you have the explicit translation symmetry, right? So it's a partial derivative. So you can think of, I mean, if you consider four momentum, then you have translation in the time direction, translation in the position space. So for the standard S matrix has the translation symmetry explicitly. But on the other hand, this boost eigenstate, we have explicit Lorentz symmetry. That's the key difference. But we know that Lorentz symmetry from the Poincare symmetry, and also translation is coming from Poincare symmetry. So the point is the standard of momentum eigenstate, we have the translation symmetry manifest, but in boost eigenstate, we have the Lorentz symmetry manifest. That's why we have a Lorentz symmetry, some of the conformal symmetry in boost sphere.
With this, those boost eigenstate, can you also have unitarity?
Unitarity is not clear because because we are talking about I goes to infinity, T goes somehow infinity, and the locality and those time, the concept of time is still unclear. So yeah, people try to understand that one, but yeah, there is no clear answer for the unitarity.
Okay, I have a question. So you mentioned the boost eigenbasis, right?
Yeah.
So are you considering the boost generator eigenvalue or?
Yes, I mentioned the K3. So K3 is somehow the K1, K2, K3.
So you think well defined quantity? Usually boost operative is subtle, fine.
Subtle.
Yeah, to define boost generator. In field theory, usual field theory.
In what sense? In what sense?
Yeah, if you consider the boost generator in terms of energy momentum tensor, you contain time and something explicitly.
So what I mean, boost eigenstate somehow, I just mentioned that this K3 is somehow some partial differentiation. We know that it explicit form for this one, and big phi, small phi is given by the function of this x0, x3. So you can simply compute the eigenvalues. Yeah, that's what I know. But yeah, so you can, after you compute these things, then you get some eigenvalue times the wave function. So in that sense, this boost eigenstate that. But in 2D compound field theory, you know that it is well known that the highest weight state somehow the weight should satisfy this condition. For the positive modes should vanish, and the negative mode, the particular condition still we have the zero. But if you consider only this piece, that should have some concrete eigenvalues.
So boost is in 4-dimensional motion.
Yeah, 4-dimensional motion.
In boundary theory, it's L0 plus L0 bar.
Yeah, that's right.
Energy.
Yeah, this boost and this I mentioned that the dilation. Yeah.
Where are the other generators? You mentioned infinite dimensional.
Yes.
It's a finite.
Yeah, so we are talking about here only the Lorentz generators, right? So in terms of this is the 6 generators. Other one you can basically somehow from the standard the 2D stuff in here. So one can imagine if you just remember bilateral algebra, then you get some any power of this one and partial derivative, then they will give you the infinite number of generators. Yeah. For example, we can go on this is only the L0, L1, plus minus 1, but you can, if you just remember the mode expansion for the Virajora case, then you get 2, 3, 4, 5, and so on. But that is related to the previous set to some power and partial derivative.
As for the other generator, is there any central charge?
There are no central charge in node.
No.
Central is, yeah, Virajora, yeah. I think the BMS context that there is, I mean, they have found some explicit form for these generators, and they satisfy so-called BMS algebra. So I will mention maybe the next context and. Okay, so in section 4, I will describe the celestial amplitude and celestial operator product definition. Okay, so if you go to the Afghan's textbook, you can see that this Mellin transform, and also the Mellin transform appears usual ADS-CFT context by saying that, I mean, the boundary and bulk Feynman propagator, then also so we have some experience in this Mellin transform, but the definition is it's very simple. So you simply, for given f, you just multiply this factor and then integrate 0 to infinity, then you get some expression. And also the inverse transform is present. And this is a standard OPE in 2D CFT. Yeah, so we are interested in this observable amplitude that is related to our this transition probability. So we can introduce this kind of notation as matrix. So by multiplying this Mellin transform factor, we have some different amplitude, different bases. So you have here again, and by integrating over all omega j's, then we are left with, we don't have any omega dependency in here. So capital delta appears in this way. And also, if you have some helicity in here, then that helicity is somehow encoded this big J1, Jn, and so on. 2D case, this is the usual 2D correlator. Okay, so this is somehow I mentioned the previous drawing. In here, somehow this is somehow the standard momentum eigenstate. We have some scattering problems. So we have the past null infinity and the future null infinity in here. They are entering into this one and they are scattered in this direction. And so we are talking about the massless particle. So that can be interpreted as these two spheres in here. So at the origin we are here, and I was infinity limit. We have some boundary surface, and you can see that this incoming case, we have the 3 cases in here, and this outgoing one in here. So that can be written in terms of this 2D correlator. So by applying those Mellin transform for the scattering amplitude, we get this one. So this is in that sense, this is equivalent to each other.
What is the main motivation to take Mellin transforms?
One of them is we want to make sure that Lorentz symmetry is manifest, and also in the context of the conformal symmetry or Lorentz symmetry, we need to have in order to understand the representation, we need to have a highest weight representation. So in that sense, also those are necessary for the Maillard transform. So I didn't say anything about at the beginning. We don't know what this power means in here, but it turns out that this is related to the boost weight. That's the point. I think this is not just change of the basis. I mean, there's more than that. I mean, that's what people try to understand this celestial stuff. Yeah, so let me just repeat in here. So, momentum space amplitude, the standard one, is going to celestial amplitude for the S matrix goes to the correlator. So as I mentioned before, somehow the celestial amplitude somehow conformal symmetry manifest or Lorentz symmetry manifest. On the other hand, the standard conventional momentum space amplitude somehow the translation symmetry manifest. That's the big difference. Okay, then we can go on the celestial phi. Okay, so from the standard Feynman computation, Feynman diagram, this was done recently, so in the community of the celestial holography, and they found somehow in the phenomenology we have some collinear divergences. So collinear means the two external particles, they are perpendicular, they are parallel to each other. So in that case, we have some divergence appears in that amplitude. So that can be encoded, they can be interpreted as a singularities in 2D celestial OPs. This is some non-trivial observations. And if you just rewrite those propagator and vertex, and then those combination, basically pi plus pj complete square is equal to we are talking about a massless particle, the null momentum. So we have only the cross terms in here. So if you using this the different kinds of bracket, then this somehow is proportional to our difference Zi and Zj. So for fixed Z bar, this means the Zi goes to Zj in the 2D case. And then so it's a simple for in here, and basically we will end up with this kind of this is the boundary two operators. The OPE is given by this one, and the remaining part is some other detailed explanations for the so the collinear limit, we have this kind of behavior. So for example, the amplitude is given by those split factor by another amplitude, and this amplitude, so we consider pi, pj particle, they are collinear, then we have small p and small pi, small pj behaves like capital P. So those are replaced by capital P, and we have the split factor, depends on the summation in here. So we are talking about the graviton case, then this should be +2 or -2. Okay, so now then this is some detailed relation. So it turns out that the collinear divergences is equivalent to have the holonomic limit. So Zi goes to Zj. Okay, then so this implies some singularity of the OP in here, and this is our previous change of variables. And then the Taylor is one of the authors in Park Taylor. If you just study the amplitude paper, then those Park Taylor paper is very well-known paper, but one of the authors are in here. This was done recently, so it's 2019. So split factor is given by this explicit form, and then we this is some details for the other cases. Is the graviton, and we have the virtual graviton splitting two collinear gravitons, and in other cases we don't have any singularity. So the Berlin transform somehow play the role of in this construction, and I just take this Euler vector function from the mathematical, so you can easily see that this Euler vector function contains two variables x and y. So the point is, if you just consider zero value in x, y, zero, in also negative integer, then you get this infinity structure, this known fact. Therefore, by taking those complete different change of variables, we are left with this some integral that is related to the previous Euler vector function. Okay. Therefore, in summary, for the graviton case, we have +2 helicity, +2 helicity, and this is the usual OP terminology. We have weight, boost weight delta I and delta J. On the right hand side, you have also same helicity for the graviton, and you have the kappa is given by square root. Inside the square root, we have the gravitational constant, the simple pole structure 1/Zi minus J. And this is the Euler vector. And similarly for the gluon case, Yang-Mills case, you get the similar split vectors in here and here, and also we have some collinear property, virtual gluon, and so on. Then we will end up with this kind of explicit OP structure. So you get A, B, C is a group indices, and you have the boost weights in here. Here is the +1, +1, and +1 on the right hand side, and structure constants, and also we have the similar Euler beta function on the right hand side.
In the gravity case, you didn't specify gravitational theory at all, but somehow asymmetric is fixed.
What I'm saying is Einstein plus Yang-Mills theory, what I'm doing in here. So
Where did you put that input into Einstein gravity rather than scalar gravity?
In first part, also you introduced the matrix from the classes.
Oh yeah.
So that is, I think that is something related to the flat and plus something.
Yeah, so I'm asking
And
that something extra. It's a metric based theory, but it can be a scalar theory there.
yeah. So in the case, each tensor equals 0, so Einstein equals 0, but non-zero complement tensor, by tensor. So likewise, the gravitational wave, so vacuum solution plus something. But in this case, it does not show that the matter part. It's only take the metric, the ansatz as one of the assumptions. So that ansatz describe the something R and R which tends equal 0 plus non-zero by tensor. It looks like the gravitational wave.
No vacuum, you are saying.
Maybe but in Bulk space time does not have the knowledge. I'm not sure, but in Bulk it's R equal infinite effect or something. Physics is R equal infinite space.
Yeah.
Infinite. So and also consider the Lorentz symmetry. Yeah. So it could do something. I think that it is one of the try to understand the gravitational wave in terms of the particle physics. So at graviton.
Yeah.
Like that.
Yeah,
I could not understand why it was a graviton. And
that's Einstein. Yes, I didn't mention that he mentioned the gravitational radiation. I mean, I mentioned that M, N, and capital C. So that C is related to gravitational radiation, and
I understand the gluon that group. Is it a song?
So you are thinking about some Lagrangian, right? I think it's Lagrangian.
But what I understand is that we can start with just Barker theory or Einstein-Hilbert action and some Yang theory, and then we can get the solutions for all the fields. Then we can apply the asymptotic limit to r equals to infinity. Then actually we can get some asymptotic solutions for all the fields.
including Yang.
Yes, it's including Yang and the gravitational degree of freedom. So in this case, actually, these solutions are toss-ups, Professor yeah.
Without considering asymptotic freedom, which is actually quantum mechanical phenomenon. In short range.
Okay, this is some of the technical facts on the Euler beta function. So what Streninger and his collaborators did was somehow by looking at either this one or either look at this one, you can just simply remove those infinity behavior by multiplying the so-called soft limit. So in that computation, we need to use this explicit relation. So this blue one go to the left-hand side, and this one go to the right-hand side, and we are left with only this usually binomial coefficient. And also we can understand the previous OP structures by using the different method, and also we can just skip this part, but let me just mention that this is the standard momentum eigenstate basis. We have the amplitude and we have the Berlin factor in here. This is another celestial amplitude, and we have the usual the relation between left right weights in terms of the previous conformal weights and the spin in 2D case. And then we can associate with this according to previous discussion. Then this 4-point amplitude can be written in terms of, this is usually the momentum conservation from the Feynman rule, and maybe you are familiar with this Rocking notation. This somehow known the amplitude expression, and this is left to right spinor notation. So you can see that the jet dependence appears by taking the ratio. And this is somehow detailed explained and the explanation, and using this change of variables, you get basically we are left with this kind of relation. So you just simply inserting this expression in previous expression, then we get finally this kind of relation. So it is 1, 2, 3, 4, and here is a 1, 2, and some 3 plus 4. Then the common factor is 1, 2, and then we can read of 3, 4 OPs from in terms of on the right hand side you have single operator. So we will end up with this kind of previous expression for the Cologne case. So you get 1 over z is a simple 4, and I just expanded by using the Taylor expansion. This is usually the Euler beta function.
Proving this.
Yeah, proving this. Yeah.
So I have a naive question.
Yeah.
Actually, in non-abelian case,
Yeah, none of it.
the physical quantity should be gauge singlet.
Yeah.
Singlet.
Yeah.
But in this case, actually, there appear many group index. So is it physical? physical amplitude, physical OPE.
So you are worrying about this, the index, the structure of index.
Structure dependent. So physical OPE or. So as you know, in Holography monopole, the physical sector is a U, I think, you know.
That what you mean by that? Then what's the meaning of this ABCD indices, right?
Yes.
So when you consider splitting and amplitude, your color index also skip. So for considering splitting amplitude, there is the splitting amplitude, then again probably it does not make, it does not make problem. I mean, the similar thing is when you consider the Yang case, the computing the color index and color free index and color index is the scattering amplitude relation is related with trace of those color index ABC. But the similar thing happens when computing those things in Celestial.
Yeah, what he's saying is, I mean, we can take some trace.
Trace.
Yeah,
So we have to single out the physical.
yeah, that's it. Okay, so this is for section 4, and let me just, I will finish until the 6 p.m. So still 15 minutes, so yes. Okay, so soft theorem was found by this, the known physicist Weinberg in 1965, the reading soft. Actually, he considered somehow the graviton case, and you can think of maybe by inserting this graviton in the incoming outgoing incoming external lens, or can combine these internal lines. So the subreading soft theorem was found by Hachacho and Streminger. Hachacho is somehow the student of BAFA, and he moved to IAS, and he constructed the so-called BFCW. So one of the authors is Hachacho and Streminger. Yeah. Okay, so the soft symmetry, soft theorem can be described by the following form in here. So we are considering somehow the n+1 amplitude. So 1 is the previous additional external scalar particle. So we have this the energy is given by omega, and we have some polarization terms. So we are talking about the graviton. Then this omega goes to zero limit. You have the 1 over omega term and one omega zeros term and omega linear and omega term. So multiply by here is n amplitude. So we don't have this n+1. It is without these soft particles in here. So in other words, if you consider the addition of those soft particles can be described in this way, and we have the whole thing is given by soft factor multiplied by amplitude, but without any those soft components. Okay, then this is another explanation. So we have low energy. So soft particle means we take the energy goes to zero limit, but without those massless particles, somehow soft limit is related to two different amplitude. And yeah, so that now it comes out the soft theorem, and this we are talking about asymptotic symmetry. So this is somehow the relation between the two different results. This is Weinberg's theorem, and subreading case, we have also the similar behavior, but in this case, we have the superrotation. This is super translation, subreading is superrotation. And yeah, so, and also there is some technical things in here, but we need to somehow diagonalize these operator value weights, and we need to somehow introduce the so-called the boost basis I mentioned before. This is, if you just look at a CFT textbook, that you can easily see that by acting this T on the correlator, you will end up with this well-known primary condition. So this whole thing, in order to have the zero, then this correlator relation is so-called word identity. And then, yes, for the subreading case, we have this superrotation asymptotic symmetry error can be interpreted by adding this stress sensor. For the photon case, we have the reading soft theorem, and graviton case, we have the reading and subreading. So we have BMS super translation. I mentioned that the extended BMS is nothing but BMS super rotation and so on. So Lorentz generator is given by this kind of action in here for given the boundary operator. And for the translation, we know that we mentioned that omega, the scale for the scale for the null momentum vector, we introduced omega. So omega plays a role over in the form of the integration of the Mellin transform. Somehow that changes the boost weight. So that's why we have, for given HY is changed by this one and this. Somehow you can also see that those extra vectors. Okay, so now the previous question was how do we see that those infinite symmetry? So for example, in this case, extended BMS, we have in here we have the KL belongs to plus minus 1/2. So this is, I mean, we have only 4 cases. So, and also in previous Lorentz case, we have 0 plus minus 1, but we have the infinite number of modes in here, and also the translation case, we have we allow the KL range for any integer and happy integer number, then we will have infinite number of P and infinite number of L and so on. So that's what I mentioned in here. So M and KL in here. So we have the infinite number of generators. So this, yeah, so the BMS is given by Lorentz semi-Dirac product super translation. Extended BMS is super rotation or Virasora semi-Dirac product and super translation. And this is somehow the some details for the supersymmetric case. I mean, this is related to my recent work, and extend super BMS by this group. Yeah, and also the extended BMS case, we can allow all the moves, and you get the explicit commutator relation. This I didn't write down all the indices in here. For the supersymmetric case, we know that we have, for the graviton, we have the gravitino. For the gluon, we have the gluino, and also yeah, and so on. And let me just describe what this means. So we for the celestial operator where one can introduce this, the standard basis object. So we have integral over the omega. Okay, so then we have the celestial operator characterized by delta and j, and also it depends on two angular coordinate in two sphere. And we expand these things, and then we have somehow so-called soft limit in here. So by using this delta function behavior, so on the one hand, we have the 2D language. In terms of 2D language, delta was minus n can be interpreted as, can be described as the omega is somehow the standard momentum eigenbasis notation. So we have this kind of correspondence in here. Okay, so yeah, so delta 1, 0, -1 is leading, subleading for the soft graviton case. We can introduce 2,2 Klein space in here. SL12L, SL12R in here, and I mentioned in the previous the section, we mentioned that this one, and then we can so we have the soft graviton expression. Then you can just multiply both sides by taking this integral. Then you can easily see that the power is located in the denominator and numerator in here. So that's why what I mean in here is a pole of 1 over omega in the momentum eigenstate. The omega is somehow the energy can be interpreted as in 2D language. That means we have the 1 over delta -1 in here. So by using this dictionary, one can understand all the structures behind the symmetry structure. And this is another way to obtain the previous OP, the boundary operators in one. Okay, so now this is the same as the previous one by using the different notation, but basically we have on the right hand side we have the Euler beta function. Okay, and then we can take the soft limit by taking, I mentioned that the Euler beta function has some particular infinity structure. So we can take this one, then we can remove all the infinities in the corresponding OP, and we have the conformally soft graviton has the following the OPs. So you can see that on the right hand side, we have only the binomial coefficients. So there are no infinities, and we have some coupling, and also 1 over z, the simple pole structure and derivatives on the right hand side, and this is KL also appears through the previous relation. So we can have the bold expansion by using the usual safety technique, and we introduce this kind of some transformation. Then we will end up with the known commutator relation. For the P equals 3R, P equals 2, and P was given by the previous the relation in here. Okay, so this I mentioned for the graviton case, we have the J2 in here. So in the soft limit, we need to have this epsilon factor in order to have vanishing of those infinities. But the Euler beta function, we have the infinite number of infinities. Again, I just repeat in here, you can see that this x minus k, y minus l goes to on the left-hand side, and x plus y minus k minus l goes on to right-hand side, and you get the previous relation. Okay, so by using the contour integrals, we will end up with one of the commutator relation is given by this one, and also this is another picture. And yeah, so I just moved to 2D CFT, we have the W algebra developed by the Jamolojkov. And we have small w, capital W, infinity, 1 plus infinity, and so on. So you can see some review paper in here. My recent paper is given by this one. This I mentioned already, Stranger's paper. And yes, according to this group, they developed somehow extended super BMS algebra. So among them, we have in my paper, we introduced this gravitino-gluino case. And yeah, so returning to the old work by this Pope group, topological double infinity algebra. So that is somehow related in this construction. So this is results by the Streminger's work. So we have the 3 commutator relation. Moreover, we have another 4 commutator relation. That's what I did in this paper. And also Bacchus, this is so-called the wedge algebra of the W, small w 1 plus infinity algebra. So the particular in here, and I think he visited SNU maybe 90, something like that. But he passed away. And let me just conclude the final part. So we have so what about the relation between the string world sheet and also massive particle and also one loop level? We should understand what's the structure of the celestial CFT. And he is the amplitude person, and he wrote some paper by using the mathematical program. And last October, Schwartz also mentioned that some open problem type 2B, type 2A on T6, T7. Yeah, still we are talking about the flat space. If we are familiar with the twist approach, then also you can look at and basically this holography somehow on the one hand from the Penrose and Newman, and also Penrose somehow studied this kind of work in very long time ago. And also the Corellian amplitude somehow related to this flat space holography. So in this case, we have 4D, 3D relation, the experimental observation, gravitational memory, spin memory, and so on. And he mentioned that the unitarities are still locality, and concept of time is still not clear at the moment, but somehow maybe near the black hole we cannot ignore the quantum effect. So this will be somehow another motivation. And this is another triangle, the previous triangle. So let me just finish my talk by looking at this last slide. So from the Stranger's triangle, we have this kind of 3 objects in here. But at the moment, we don't know yet experimentally how the gravitational memory effects appear in the nature. So this is question mark. So LIGO, Lisa, and maybe people who were very ambitious about the possibility of this one. Then recently, Maldason and his collaborator mentioned that some relation between these M theory and this soft theorem. So in that sense, I can say that maybe one of the evidence of string or M theory directly or indirectly in our real world is somehow to find out this possibility and find out how do we observe this gravitational memory effect in in our experimental setup. Okay, so I will finish here.
Question.
I mean, BMS or this symmetry does not require string theory, and suddenly while you are talking, that it will be the evidence for string theory.
BMS symmetry, it's coming from asymptotic symmetry, right?
Yeah.
And then at the four-dimensional sense, we can go the soft theorem. By the work of the Streminger and his collaborator, and the recent paper by the Maldasana and his collaborator, he just observed that the soft theorem in the matrix theory. In other words, 11D, or if you just compactify that, that's the 10D theory. So this is somehow one of the result why the string theory or M theory can be go through in this way, and maybe.
I mean, this is just so the string theory can have also this all this phenomena, but without referring to string theory, still there is a memory effect. And
yeah, so my opinion is if one can find this gravitational memory effect, then we can go through in this direction, in this path. Maybe that can be explained by string theory. So that's why.
that first arrow should be just one way, not a mutual way.
Oh, this arrow.
Yeah.
That's
물론 말대사나가 물론 그 한 논문 자체가 하여간 굉장히 급하게 쓴 거는 맞긴 한데, 물론 옛날 사람들이 소프트 시어럼 갖고서 샘 같은 사람이 뭐 스트링 시어리 어떻게 나오겠냐 얘기를 했는데, 이 말대사는 이 얘기는 좀 더 뭔가, 물론 이제 그 스캐터링 문제를 그냥 4차원에서 계산했는데, 그래도 뭔가는 BFSS 모델에서 했다는 거는 좀 새로운 측면이 있고, 그 다음에 스트링저 그룹이 이미 그거에 대해서 일부 몇 가지 논문이 나왔었는데, 그거는 모르겠어요. 그 스트링저 톡을 들어보면 최근에 그 KITP에서 한 거 보면은 뭔가 지금 생각을 하고 있는 것 같아요. 스트링 티어리에서.
Theory of everything, everything.
soft theory.
네, 질문이 있는데요.
예.
Celestial Holography가 다른 차원에서잖아요. 제가 기억하기로 크롭 컨디션이 4차원하고 다른 5차원 이상하고 달라가지고.
근데 보통 D 디멘전하고 D 플러스 2하고 D를 얘기는 하긴 해요. 그러니까 폼이라는 사람이 한 것들.
크롭 컨디션이 다른 걸로 알고 있거든요. 웨이션에 관해서 4차원하고 4차원 이상, 5차원 이상하고는 완전히 달라서.
예.
그래서 이게 성립하는 거지. 그러니까 소프트웨어하고 디멘션에 무관한 거 아닌가요? 근데 이 BMS 타입의 그 슈퍼 트랜스포레이션하고 슈퍼 로테이션이 다른 차원에서 정의가 안 될 것 같은데요. 이 플러스파는스가 4차원에서만 성립하는 거 아닌가?
아니요, 근데 BMS3도 있고 BMS5도 사람들이